Hi viewers. What I'm showing you in this short video is an attempt to electrolyze water. I have two sections of graphite felt, commercial graphite felt. Each has been lightly nickel plated to boost conductivity, to increase connectivity. So electroplated nickel. We've done scanning electron microscopes, microscopic examinations. So we're going to use magnesium sulfate, Epsom salt, as a standard electrolyte. We're using 2.6 molar magnesium sulfate, heptahydrate, and it's not a so-called water in salt electrolyte, WISE is the acronym, but probably on the borderline of being such a material. We're at 20 degrees Celsius, plus or minus a degree, and I am looking for a water-based electrolyte as a standard when I build test supercaps. And our focus is on composites, graphite felt composites. Activated carbon, some carbon black perhaps, binder, white halloysite, which is low iron, and it is nanotubular and rather inexpensive. Our material is provided by Applied Minerals Incorporated in Utah. They have a quarry there. I did not sieve the material. I used it as is in composites. Now, I won't be showing you that in this video, but they're back here. And that's our main focus. And on developing composite, graphite-based composite electrodes for supercapacitors. So I want a high water electrolysis overpotential. Now, if you're working with generation of hydrogen oxygen gases from water, you want, of course, low overpotential, 1.23 volts, ideally, to electrolyze water. And it is ironic for me, at least, that for a number of years I was working on water electrolysis and trying to keep the voltage down to 1.23 volts. Now with supercaps, I want to go the other way. In other words, I don't want to produce hydrogen oxygen gases. And there is a lot of advantages to using water-based electrolytes. And right now, 2.5 volts. And my DC power supply here, which is very cost effective, I got it on Amazon. For me, it was about $35 US dollars, and I don't pay postage here. And 2.5 volts, constant voltage is being applied by the power supply. And the current is vacillating between 0 amps and 10 milliamps. So let's say I'm seeing about 5 milliamps. I'm still not at equilibrium. This has been running about a half an hour. No gas evolution being observed. And that's exactly what I want. 2.5 volts would be just fine. Instead of playing with ionic liquids, deep eutectic solvents, classic water and salt electrolytes, which each one of these types has its own problems. Flammability, toxicity, impurities. So this would be fine. Once again, 2.6 molar. It's about 65 grams of Epsom salt in a total of 100 milliliters of water, a little at a time. Homogeneous solution. We didn't measure the viscosity yet, but I've worked with deep eutectic liquids that are far more viscous. So that's where we're at. And I still think in about a half an hour, I'll be down less than 5 milliamps at 2.5 volts. And this is graphite felt, lightly nickel plated. And then what follows will be composites. Because magnesium plus 2 has its own problems. Passivation, formation of magnesium hydroxide on the electrode surface. But I will tell you that carbon-based electrodes and magnesium sulfate in water, it's unusual. And I believe with the halloysite, I'm going to be silanating, and I believe I can keep the passivation of magnesium hydroxide to a minimum so it will not interfere with cycles of charge-discharge. One of my students will be giving a talk this month at the National American Chemical Society meeting in Washington, D.C., and she'll be disclosing some of the work she's done. She'll be graduating in December and going on to graduate school. And I'm emeritus now, but I'm still doing research, and I enjoy working with some undergrads that are interested in this area. And we'll be fabricating carbon-based electrodes here at school as well. Thank you for watching. We'll keep you posted on what's going on. David S. Soriano. If you go to ResearchGate, you can see some of my preprints on supercap work. Bye for now.